Hello everyone. Today I have going to deliver fourth lecture. The topics are concept of a strains, normal strain, shear strain, a strain tensor, principal strains, constitutive law, mechanical behavior of solid materials, elastic behavior, viscous behaviors, viscoelastic behavior, and elastic behavior, stress relaxations, creep, plastic behavior, Hooke's law, principle of superpositions, and set Venant's principle. So now let us start concept of a strain. Pure deformation of a body is characterized by a change in its size or shape or both. For a quantitative equations of deformations, we introduce the concept of a strain. As can be easily visualized, a line segment either inside of the body or on its surface will in general change its length and orientation of the deformed geometry. In order to take into account these two changes separately to kind of a strain, namely normal strain and shear strain. So now first of all, I go to define what is normal strain. So normal strain is defined as the ratio of change in length of a small line segment to its original length. Suppose that a line segment of a small original length L0 in the undeformed geometry has a final length LF in the deformed geometry. Then the normal strain is given by normal strain equal to LF minus LO divided by LO will be equal to your del L0 by L0. So where del L0 is the change in length. Obviously, a strain is a dimensionless quantity. It is positive if there is an extension of the line segment and negative if there is contraction. So equation 1 gives an average value of normal strain for a finite length of the line segment. By analogy with the definition of a stress at a point, a more precise definitions of normal strain can be given with the help of limiting process, and then we have the normal strain at a point P in the directions of PQ shown in figure 1 as a strain PQ is equal to limit PQ tends to 0 P dash Q dash minus PQ divided by PQ, where PQ is a small line segment in the undeformed geometry which occupies the position P dash Q dash in the deformed geometry. So it is important to note that the normal strain at the same point P in another directions is in general different. It may also be mentioned here that equation 1 and 2 give identical value of normal strain PQ in the case of homogeneous deformations of a body. If the displacement field is such that its components are linear functions of the coordinates of the point, the body is said to have homogeneous or affine deformations. In this case, the state of a strain is the same at all the points of the body. So after defining the normal strain, now come to define here the shear strain. So shear strain at a point of a body is defined as the change due to deformation in the angle between two or small line segments that were originally at right angle. This would be the shear strain in the plane of the line segment. So figure 1 shows two line segments PQ and PR at a point P in the plane A, and they are at right angles in the undeformed geometry. The point P, Q and R occupy new position P dash, Q dash and R dash respectively in the deformed geometry. In displacement of the points are very small through they have been exaggerated in the figure. As a result of deformation, angle Q dash, P dash, R dash is not a right angle, and the change in the right angle is the shear strain. Shear strain QPR, that is shear strain QPR equal to angle QPR minus angle Q dash P dash R dash. So mathematically speaking, however, the shear strain at point P in the plane QPR is given by angle of shear strain QPR equal to limit PQ tends to 0 and PR tends to 0. So angle QPR minus angle Q dash, P dash, R dash. The shear strain is expressed in radians and is taken as positive if the angle between the small line segment has reduced from pi by 2. The Cartesian components of a strain, similar to those of a stress, can be given as follows. Consider a triad of very small line segments PQ, PR and PS oriented along the axis X, Y and Z respectively at a point P in the undeformed geometry of a body. So when forces are applied to the body, let the line segments move to new location P dash Q dash, P dash R dash and P dash S dash respectively as shown in figure number 2. Then by the definition of normal and shear strain and following the same notations as for a stress components, we get normal strain in x-axis will be equal to limit pq tends to 0 p dash q dash minus pq by pq. Normal strain in y directions limit pr tends to 0 p dash r dash minus pr by pr. Normal strain in zz direction equal to your limit ps tends to 0 p dash s dash minus ps by ps. So now come to shear strain about xy plane equal to shear strain about yx equal to limit pq tends to 0 and pr tends to 0 pi by 2 minus angle q dash p dash r dash. And shear strain about yz equal to shear strain about zy equal to limit PR tends to 0 and PS tends to 0 pi by 2 minus angle R dash P dash S dash. Now shear strain about ZX plane equal to shear strain about XZ will be equal to limit PS tends to 0 and PQ tends to 0. So angle pi by 2 minus S dash P dash Q dash. So now we wish to relate the strain components given in equations 5 with the Cartesian component of displacement, that is ux, uy and uz of a point P. For small deformations, we may assume that P dash Q dash and P dash R dash lie in the xy plane as shown in figure 3. So then assuming a continuous displacement field, we can write the x component of the displacement of Q, that is the component of QQ dash along x-axis as ux plus del ux by del x pq. So from equation 5a we have normal strain in x-axis equal to del ux by del x. Similarly, the y displacement of r would be given by uy plus del uy by del y pr. So from equations 5b we get normal strain in yy equal to del uy by del y. So referring again to figure number 3, the y displacement of q would be given by uy plus del uy by del x pq and the x displacement of r by ux plus del ux by del y pr. So thus change in original right angle qpr, that is shear strain about xy from equation number 5d will be given by shear strain about xy equal to shear strain about yx equal to del ux by del y plus del uy by del x. In a similar manner, we can write the other component of a strain as normal strain in zz is equal to del uz by del z. Shear strain about yz is equal to shear strain about zy equal to del uy by del z plus del uz by del y. Shear strain about zx equal shear strain about xz plane equal to del uz by del x plus del u x by del z. An important features of equation 6 is that the strain components depend on the rate of change of the displacement and not upon their absolute values. If the components of a strain associated with a certain set of axes are known, it can be shown that these components are necessary and sufficient to determine the strain components with respect to any arbitrary set of axes. So after the completion of your strain, normal strain and shear strain, so I have go to just shown here one physical problem and then basically solve in the ANSYS. And so what is normal strain and what is shear strain, you have to calculate. So I have go to calculate in the ANSYS softwares, and after the calculations, so this is my results shown in your graphics area. So this is especially shown in your graphical area as normal strain and shear strain of these components. So after the solutions, so here show the results value. So normal strain in your x direction, normal strain in y, and normal strain in z, and shear strain about your xy plane, shear strain about your yz plane, and shear strain about xz plane. So this is your basically of the nodal solution, and shown here the all strain value. So you have to calculate it inside of the ANSYS. And so how to calculate and how to find out these results in ANSYS, so I will teach you in further. So now the explanation of your normal strain and shear strain. The next topic is your strain tensor. The set of component of a strain which may be written as in matrix form as constituted is called the strain tensor. So normal strain in x direction, so shear strain about xy plane by 2, shear strain about xz plane by 2, and shear strain about yx plane by 2, normal strain yy, shear strain about yz plane by 2, shear strain zx plane divided by 2, shear strain zy plane divided by 2, and normal strain in zz direction. So notice that the shear strain terms have been halved in order to help make component of a second order tensor. And now after defining the strain tensor, go to the define here the principal strains. So principal strains and their directions can be defined analogous to the principal stresses and plane. So thus at any point in a body, there is at least one trait of line segments, of course of infinitesimal lengths, which does not lose its orthogonality as a result of deformation. The three line segments undergo either extension or contraction. The directions of these line segments are called the principal directions or axis, and the normal strain in their directions are known as principal strain. It is obvious that the shear strain components are zero with respect to the principal axis. The strain matrix associated with the principal directions can be easily written as normal strain in 1, normal strain in 2, normal strain in 3. So all shear strain value is 0. So where normal strain 1, normal strain 2, normal strain 3 are principal strains. So after the completion of the topics a strain, normal strain, shear strain, a strain tensor, and principal strain, I have go to discuss and briefly explanation of constitutive laws, Hooke's laws, principle of superposition, Venant's principles. So now let us start constitutive law. In first point is the mechanical behavior of solid materials. So in the preceding sections we discussed a stress and a strain as separate distinct entities, and we did not require any assumptions regarding the material behavior of the material or its nature, except that it was continuously distributed in the body. So it may be intuitively clear that a stress and a strain cannot be independent of each other, and there must exist a definite relationship between them for a particular behavior. So these stress-strain relationships depend upon the constitutions of the material, and hence the law governing them are called the constitutive laws. So now present below some of the idealized behavior of solid materials. So point number 1 is elastic behavior. If the deformation of a body is such that it disappears, that is the body recovers its original undeformed geometry instantaneously upon the removal of external forces, the material is said to be elastic. Most of the engineering materials exhibit elastic behavior within a certain limit of load called elastic limit. No real material is perfectly elastic. Elastic behavior may be either linear or non-linear. A linear elastic material obeys Hooke's law. So that is, the deformation is proportional to the force producing it. The second point is the viscous behavior. So in this case, the material behaves like a viscous fluid. The deformation rate with respect to time rather than deformation is a function of load. Even if the load is maintained constant, the deformation increases with time and upon the removal of load. The deformation does not disappear. Solid materials under dynamical and or high temperature and or long time stress conditions usually exhibit this fluid characteristic. Viscous behavior is either linear or non-linear. So now the third point is viscoelastic behavior. If a solid has a combination of viscous and elastic characteristics, not necessarily linear, it is said to be viscoelastic. Metals at high temperature and polymers generally behaves viscoelastically under load. The behavior of such materials is represented by a time-dependent relation between forces, stresses, deformations, strains, and temperature if the body is subjected to a varying temperature field. Some of the viscoelastic behaviors go by their popular name as given below. So first number is your anelastic behavior. So in this case the deformation is not instantaneously recovered upon the removal of load. It takes some time for the body to recover its original deformed geometry. As such, this behavior is known as the displayed elasticity. The second is your stress relaxations. At sufficiently high level stress level with the deformation maintained constant, the force required to hold the deformation decreases with time. This mode of viscoelastic behavior is called a stress relaxation. The next is your creep. At a high temperature with respect to the melting point of the material, the deformation increases with time even if the load is maintained constant. Upon removal of the load, all the elastic deformation disappears instantaneously. Some other deformations is recovered over a period of time, but a part of deformation still remains non-recoverable. This phenomenon is known as creep. So next is your plastic behavior. Deformations which a body retains even after the removal of loads are called plastic deformation. The behavior of a material to yield permanent deformation is called the plastic behavior. It depends upon the applied load and is independent of times. Most of the engineering materials exhibit plastic behaviors beyond elastic limit. Plastic deformation is more complicated than the elastic one. For example, in the plastic range, there is no simple and definite relationship between a stress and a strain as we have for linear elastic deformation. So now the next is your Hooke's law. So Robert Hooke was the first man to announce the notion of elasticity based on his experiments on a spring under load. He remarked in 1678 tensio sic vis, which means that the stretch of any springy body is as the force applied. Since that time, the above noted indefinite law has been given more precise mathematical form. However, the constitutive law of a linear elastic material goes by the names Hooke's law. It can be stated as the displacement of deformation of any point in an elastic body, of course linear, is proportional to the force which produces it. For most of the engineering materials, Hooke's laws hold good within a certain limit of load, which is called the proportional limit. Thus, if a body adequately constrained to prevent any rigid body motion is subjected to a force F, then the displacement U is an arbitrary point A is a particular direction is given by U equal to A multiple of the force F. So here is a constant and F is the magnitude of the force F. The value of a depends upon the material of the body, the direction and point of application of the force, the location of a point A, the directions of the displacement U and the geometrical configuration of the body. It does not depend on the magnitude of force F. So equation 1 may be extended to a linear elastic system subjected to a set of external force F1, F2, F3, Fn. In that case, the displacement at any point in a particular directions will be given as U equal to A1 F1 plus A2 F2 plus A3 F3 plus An Fn. Here A1, A2, A3, An are constant depending upon the factors listed above. So Hooke's law generally gives a linear relationship between a stress and a strain. The next is your principle of superpositions. According to the principle of superposition, the effect of a system of external forces acting on a linear elastic body is dependent of the order in which the forces are applied. The word effects has been used here in a broad sense. It implies either the displacement of deformations or internal force factor or a stress or a strain depending upon the particular cases. By virtue of this principle, it is possible to determine a particular effect due to a combination of loading by considering the effects of individual loads separately and then summing up these effects For example, if we wish to determine the displacement at some point in a particular direction due to a set of external forces F1, F2, F3, Fn. So then we have to consider that F1 acts alone of the body and we determine the required displacement, say U1. Similarly, U2, U3, Un, which are the displacement in the same direction due to F2, F3, Fn respectively acting separately on the body can be determined. Then in accordance with the principles of superposition U equal to U1 plus U2 plus Un, it should be borne in mind that the action of the separate forces of a system must be considered in conjunction with the corresponding reactions of constraints. The principle of superposition is based on the assumption that the displacement of the point of application of forces are small compared to the dimensions of the body. So after the completion of your principle of superposition, the next topic is your Van-Ant's principle. So another important principles that will be used widely in our study is due to Van-Ant. This principle in its general form may be stated as follows. At the points in a body sufficiently distant from the surfaces of application of external forces, the effects of the forces is almost independent of the manner in which these forces are applied. According to this principle, if some distributions of force acting on a portion of the surface of a body is replaced by a different distributions acting on the same portion of the body, then the effects of two different distributions on the points of the body at sufficient distance from the region of application of forces are essentially the same, provided that the two distributions of forces are statically equivalent, means that the two distributions have the same resultant force and moment. To give an idea of the distance involved, we can say, for instance, that the stress distributions found in elementary mechanics of solids for the case of a cantilever with end load will be generally correct at a distance away from the end load or the fixed end by an amount greater than the largest cross-section dimensions of the beam. Although the possibility of in its general form has been questioned by many, it is frequently used in practical application.